Hello everyone. So today we are going to see the architecture for JVM. Um, so let me just get started here. Okay. So what is JVM first? So it's you guys might have heard the term write once, run everywhere, anywhere, right? So which again is a core concept in Java. So you just write once and you can run it on any machine, any server, and that for that to accomplish that we use JVM. So JVM is nothing but a virtual machine uh, which is used to run Java programs. So I'm hoping that you guys know a little basic idea of how to run your Java programs. So for those who haven't done it yet, so once you write your Java code, you will compile that into a class file, and then that class file is what will be executed by the JVM on your operating system, or in case any operating system, right? So let's move into the architecture. So we can divide the architecture into three main components, wherein each component will have subdivisions, but we'll get it into the subdivisions part a little later. So the first three main components I would say is class. One is class loader. Second one, we have the runtime uh, data area, and we have the execution engine. We also have these JNI and native method libraries, which we'll probably get to at the last. Um, okay, so for now, just we can think of it as three different components: class loader, runtime data area, and the execution engine. And we have subdivisions or subcomponents within each of those main components. So if you look at the diagram here, you will be able to see that the class loader has three individual components: loading, linking, and initialization. Whereas runtime data area has five more components: method area, heap area, stack area, PC registers, and native method stack. The execution engine has again three components: interpreter, jet compiler, garbage collector, and again, like I mentioned, the other two: native method interface and native method library. So we'll probably go in depth in each of these components in the upcoming slides. So first, let's look at the class loader. So yeah, so before this, just wanted to um, again bring up that once you compile your Java code into a class file, so that class file will be the input to the JVM, right? So class loader will eventually get the class file as its input. So yeah, so that first thing that we should be looking at inside class loader is the loading component. Then you have linking, and finally you have the initialization happening. So we'll go in detail with each of these three components, three sub divisions. Um, so yeah, so class loader, what exactly does the class loader subsystem does? So it's responsible for loading the class file which you have compiled, and it puts it into the main memory for it to get executed. And usually the first class to be loaded is usually the class having the main method. Um, and again, this, as mentioned in the previous slide, you have three more sub components within the loading, um, which is bootstrap class loader, extension class loader, and of course the application class loader. So we'll go into each one now. First we'll go into loading. So loading again has three subcomponents. You have the bootstrap class loader, extension class loader, and the application class loader. So bootstrap class loader is its main aim or its main activity is to load all the standard Java packages. So for those who have worked on Java a little bit, might have some idea on these packages. So these might be utilities, java.lang, java.io, file related packages, and so on. So those will probably be the first things to get loaded in the memory. So that is currently being done by the bootstrap class loader. Now if you go to the second one, which is the extension class loader, this is just for loading the extensions of the standard libraries which we just saw in the first bootstrap class loader. So these are usually present in this directory, the ext directory. The third component is the application class loader, which is responsible for loading all the class files in the application class files, which are essentially the files in your application class path. Right, so this is just about the loading component in the class loader subsystem. If we move on to the next one, which is linking. So after a class is loaded into the main memory, that's where it undergoes this linking process. So linking, it's kind of combining all the classes, all the elements in different classes, and resolving all those dependencies across all those classes. So you might have used some dependencies across classes. You might be calling some other class files, variable, you might be, or method in some other class files. So this phase, I would say, is just for resolving, combining all those elements and resolving all the dependencies. So again, linking has three steps. First one is verification. So this phase is just JVM checks if the bytecode which is generated is proper, and it runs it through some validations to make sure that it's a valid class file correctness. So just basically runs it through a set of rules and constraints to check for the if it's valid or not. Right, so if we move on to the next step, which is preparation. So this is where all your static variables get memory allocations, and they have these default values assigned to them. So that happens in the preparation phase. And finally, if you move on to the resolution phase, this is where symbolic references are replaced with original references. So what do we mean by symbolic memory references replaced with original references? So if you have like references to other classes or variables present in other classes, they are resolved with their actual references. So now let's move on to the next component in the class loader subsystem. So this is the initialization component. So this is where all the initialization methods of the class, which essentially means the constructors, static code blocks, and the static variables which got assigned default values in the previous step, they will be assigned their original values here. Right, so yeah, so initialization is basically it's gonna call the constructors and static blocks and assigns the actual value of static variables here. So with this we will come to an end with the class loader subsystem. So next thing is which we're going to see is the runtime data area. So runtime data area again has 5 different components here. If you look at the diagram here, you'll be able to see that it has a method area, heap area, stack area, PC register, and native method stack. We'll probably go into each one of them in a bit. So first, let's start with the method area. So here all the class level data, right? So you might have like class level constants, field variables, methods in the class, constructors. So all those data and code is going to be stored here in the method area. And this is a shared resource, so the one JVM is going to have only one method area. So it's a shared resource. It's going to be used by, if you're handling, if your program is involving multiple threads, then all those threads are going to access um, just this one method area. Right. So next we'll move on to the heap area. So this is one of the main uh, components, I would say, which most of us might come to face or come to work with in case of any memory leaks or anything. This might be one of the things which everyone should be aware of. So this is where all the objects with their instant variables and arrays will be stored. Again, there is only one heap area per JVM. So again, it's a shared thing across all threads and everything. So yeah, so the data stored here is obviously not thread safe. So if you have multiple threads accessing a single object in the heap area, then you should take care that it's thread safe, that only one thread is accessing the object at a time, right? So let's move on to the stack area. So this is where for every thread separate stack or runtime stack gets created, and every time a method gets called, an entry is made in this area and is called stack frame. And when the method call is completed, the stack frame is destroyed. So all the local variables, again, so each thread will have its own stack. So each thread in that stack, it will have all the local variables. Again, so since this is for each thread we have a separate stack, this is a thread safe component, right? So it's not a shared resource like we saw for the heap and the method area. So it's a thread safe since it's not a shared resource. And yeah, so if you look at the stack frame has three parts. One is local variables. Again, this is just all local variables, and all those values are stored here. Operand stack, again, it's a last in first out stack, and it's used for storing intermediate operations, right? Performing intermediate operations. Then you have frame data. So all symbols corresponding to the method are stored here, right? So, and also the catch block information is also stored here. So in case of exceptions, your code might be using a try catch block or something. So the catch block, where it's used for catching all the exceptions, that's stored. The catch block information is also stored in the stack area. Okay, so that's the info about stack area. So if you move to the PC registers, so PC stands for program counter. So again, this component is basically for each thread again. So each thread is going to have its own PC register, and it's going to have the address of the currently executing instruction for each thread. So once that instruction or command is executed and it's done, then that PC register is going to be updated with the next instruction. So it goes on until all the instructions are done. Next, if we move to the native method stacks, again, this is gonna hold information about native method code, like for example, native method in the sense which are written in languages other than Java, such as C and C++. So there might be instances where you might want to use native methods just for for some other use case which Java does not support, maybe talking to the hardware and stuff like that, right? So in those cases, you might want to use um, the native method libraries. Again, some features in C and C++ uh, might not be there in Java. So in those cases, we'll be using this. Right, and also this is also for every new thread, a separate stack is also allocated. So each thread will have its own stack here. With that, we conclude with the runtime data area. Next, if we can go to the execution engine. So this is where the actual magic of execution happens, right? Here again we have three components: interpreter, JIT compiler, garbage collector. So first let's go through interpreter. So interpreter is gonna read the bytecode and execute it. So it'll read it faster, but when it's executing, it's it's slower compared to the reading process. Another disadvantage, the major disadvantage of interpreter, is that in case if you have a method and it's called multiple times, um, it will require a new interpretation each time. So that is going to be time consuming and resource consuming as well. So that's one of the disadvantages of the interpreter. The next component which we're gonna see, the JIT compiler, that helps us overcome this disadvantage. So if we go to the JIT compiler, it's gonna um, find out which of the code is repeated, right? And it's gonna optimize it in such a way that it doesn't need to interpret it the next time the same code gets executed. So yeah, so if you look at the same thing, so the JIT compiler compiles the entire bytecode for repeated code and changes it into the native machine code, right? So in that case, it improves the performance, so it doesn't have to do the same thing again for the repeated code blocks. And if you look at the components in JIT compiler, it has 4 different components in turn. So first one, we have the intermediate code generator, which is responsible for generating the intermediate code. Code optimizer, again it's optimizing the intermediate code generated in the above component to improve the performance. Target code generator converts that intermediate code into the final native machine code. Again, that's the one which is going to be run. Then you have the profiler, which is used for finding the hotspots, which essentially means it's used for finding the code which is repeated, which is executed repeatedly, so that it can optimize that performance better, right? So that's where JIT compiler comes into picture. It's essentially the component which helps improve the performance of the interpreter, especially in cases when you have multiple calls for the same method. So coming to the final component in the execution engine, garbage collector. So garbage collector, again, so once you allocate a memory to an object or some variables or something like that, so a memory is allocated to that object inside JVM. So you need a mechanism to actually find the objects which are no longer being used, so that you can remove them and you can free up the memory for newer objects or newer variables. So that's where the garbage collector comes into picture. It makes it more memory efficient by collecting and removing unused objects from the heap area. So it does its work in 2 phases. We call it mark and sweep. So the first phase is mark. So this is where the garbage collector identifies unused objects in memory. And then the next phase, the sweep phase, it removes all the objects identified in the first step. right? And this is something which JVM automatically does at regular intervals, and most probably you will not uh, need to be doing this manually. Again, so there are different types of garbage collectors in Java at the moment. So one is serial garbage collector. It's where the simplest implementation. Again, it uses just a single thread for the garbage collection. Again, this probably might be used only in small scale applications running on single threaded environments. Right. Parallel garbage collector is the default implementation in JVM. So it uses multiple threads instead of single thread in, as we saw in the serial garbage collector. But yeah, the application will still get paused uh, till that work gets completed. The third one is probably going to be the future uh, in Java, most probably. So which is garbage first garbage collector, G1 garbage collector. Again, this is for multi-threaded applications. So in this case, it divides the heap area into equal sized regions and uses multiple threads to scan each of them. Then it identifies regions with the most garbage and performs the garbage collection process on that region first. So yeah, so there's one more actually, but I haven't concurrent mark sweep garbage collector, but that has been deprecated since Java 9. And yeah, so the next one is Java native interfaces. Um, so like I mentioned before, sometimes you might need to run uh, code in other libraries, other languages other than Java, especially something could be platform specific features, or you need to interact with the hardware, or some of the constraints which you want to overcome in Java in other languages such as C and C++. So this is nothing but it acts as a bridge, between the execution engine and uh, the actual native method libraries. So in case some native method library needs to be called, it's going to be through which execution engine is going to execute all those native method libraries. Then finally you have the actual native method libraries. So yeah, these are the actual libraries which are written in other programming languages. Right, so and these will be loaded through the Java native interface, right? Finally, if we have to look at the execution flow, this is how it's gonna look like. So we have the input as the class file, like you see here, which is the input to the class loader subsystem. Inside that you have this loading phase, which is the initial one, and the bootstrap class loader is the first component where it loads all the Java standard packages. Then you have the extension class loader, which is for loading all the files under the ext directory. Then you have the application class loader, which is for loading all the application class files in your application class path. Then we move on to the linking phase, where first step is verification, where it verifies the correctness of the class file by running it against a set of rules and make sure that the class files are proper. Then you have the preparation phase, where the static methods, the static variables, in fact, are allocated memory and they are assigned the default values. Uh, the third step is the resolve, which you see here, which is for resolving all the symbolic references with actual references. And you have like the original actual values getting assigned to the static variables here. The next is the initialization step, for which all the initialization methods like constructors, static blocks, So those are executed here. Those are done here. And if we move to the stack area, the runtime data area, again we saw that it has 5 different components internally. Method area is going to contain all the class level data, or method code, method, all the class level constants. All those will be stored in the method area. Whereas the heap area is going to have contain the uh, objects, their instance variables and their data related to the objects, right? And if you look at method area and heap area, so those are shared resources. That it will be one area per JVM, so they are not thread safe. Whereas if you look at all the other remaining components, the stack area, PC registers, and native method stack, each thread will have their own stack or their own allocation inside each one of them. Right, so stack area, again each thread has it, so it's thread safe, and you have all the local variables for that thread stored there. Then you have, if for example a method is getting called, we have a separate uh, component called stack frame which gets created for each method call, right, and that will get removed once the method call gets completed. um, so moving to PC register, so this again it's for each thread, and this is gonna hold the currently executing instruction. So once the currently executing instruction gets completed, it's gonna load the PC register with the next instruction to be executed. Native method stack, and that's primarily used for executing native code, native method libraries, native method code. Again, it's per thread. Uh, then we have the flow going to the execution engine. Again, you have 3 components here: interpreter, JIT compiler, and the garbage collector. Interpreter is just for reading and executing the bytecode, right? And you have the reading is gonna be fast, but the execution is gonna be slow compared to interpretation. And the main disadvantage of the interpreter is that in case you have multiple calls to the same method, some code is getting repeated, then that's gonna need an interpretation every time. So that's one disadvantage here. So in order to overcome that disadvantage, we have the JIT compiler, which essentially looks for this repeated code blocks, and it tries to optimize it by transforming that piece of code into actual native machine code, machine language, so that the next time when that code has to be executed, it will execute it a little bit faster. Um, you have the final component here, garbage collector, so that is essentially used for removing unused objects from the heap area. Finally, we have the native method library and the native method interface. So native method libraries are nothing but libraries written in other languages, C and C++. So some features you might not be able to write those in Java. So you might want platform specific features, which might be available only in certain languages, for example C, C++. So that's where this native method library comes in. And finally you have um, the JNI, which essentially loads all these method libraries for Java to actually execute them. Right. So yeah, so these are some of the two uh, links which I found useful for um, understanding how JVM internally works. So I would also recommend you guys to go through them for your bet. So there are some examples which they have also given code snippets just to understand how JVM handles that piece as well. So yeah, so that's the end of the uh, JVM architecture tutorial. Thank you everyone.